Okay, good morning, everyone. Welcome to the second day of RSS. We have a wonderful program today as well. My name is George Papas. I'm at the University of Pennsylvania. I'll be sharing this first session. We have 5 papers on the program, but the fifth paper, the last paper, the presenter is stuck at the airport, so we'll see how that evolves. Let's get on to the first presentation, which is going to be the topic segment to regress, monocular 3D vehicle localization in 2 stages. And the presentation will be given by Jae-Sung Choi from KAIST.
Good morning, everyone. I'm the presenter, Jae-Sung Choi. This presentation is about the 3D vehicle localization using single camera. The 3D vehicle localization is the task that predicts the location and the heading of the vehicle in bird's eye view. It means that we do not predict elevation and the height of the vehicle. Traditionally, the depth from the single camera is essential to the localization. So it means the accuracy of the localization is too sensitive to the quality of the depth. So here we introduce the plane depth from the road parameters. So plane depth is just the distance to the ground. So here, as you can see here, the shape of the car does not appear in the plane depth. So given the plane parameters and 2D bounding boxes, our network projected 2D information into the 3D manner in 2 stages, so-called segment to regress. This is overall of our 2-stage architecture. I'll firstly introduce how we generate the vehicle segments from the first stage. Given the RGB image and 2D bounding boxes, stack hourglass generate the vehicle segments along the channels. Particularly, the most popularly used unit-based approach failed to generate the vehicle segments, but it generated a strongly correlated result. And this is the other example. So finally, we decided to use the stack hourglass to consecutively filter out the noise and enhance the shape of the vehicle. And as you see here, the noisy segments are filtered out. So far, I explained the first stage of our network. The following stage is the regression network, which predicts the 4 bottom corners of the target vehicle. This network consists of the 2 processes. I'll firstly introduce the fusion by normalization. This process is to fuse the plane depth into the vehicle segment using the 2 normalization layer. Particularly, it increases 9 times higher accuracy of our system. So it is very key for our system. And so far, I explained fusion by normalization. Given the fused vehicle segments, we finally predict the 4 bottom corners of the vehicle in 3-dimensional way. So here we introduce the coupling loss to impose structure prior of our network. First one is the side loss that couple the 2 adjacent points. And the second one is the heading loss to impose the coupling. And the last one is a plane loss to lie 4 points on the same ground. So without coupling loss, the shape of the bottom can be irregular, and with minimal parameterization, it suffers from the heading prediction. And with our system, it stabilizes the regression in our neural network. So here, the plane loss is effectively increase the performance of our network. And finally, we achieve the state-of-the-art performance in the KITTI dataset. Especially, we show the strong point on the hard cases, even with fast inference. This is the ablation study of our network. Given the 2-dimensional noisy input, still our network generates a stabilized result of the 3-dimensional bounding boxes. It shows the robustness to the noisy input. And given the same vehicle segments, our fusion by normalization still performed and still successfully fuse the plane depth into the vehicle segments and show the stabilized result. Finally, we propose 2-stage network by introducing the fusion by normalization and the coupling loss and achieve the state-of-the-art performance. Thank you.
The next presentation comes from ETH, and it's on Omnidirectional Aerial Manipulation Platform for contact-based inspection, and the presentation will be given by Karen Bodie.
So I'm Karen Bodie from the Autonomous Systems Lab at ETH Zurich, presenting on aerial manipulation for contact-based inspection. And we approach the challenge of aerial interaction with an omnidirectional hexacopter. Tiltable rotor groups fully actuate the system to generate force and torque in any arbitrary direction. Our interaction strategy involves a fixed end effector. With a time-of-flight sensor, we implement a selective impedance control and have local planning on unmodeled surfaces. Our experiments demonstrate our ability to perform tasks needed for contact-based inspection. So this block diagram shows that the control framework is here, consisting of a selective impedance control, local planning on unmodeled surfaces, and state estimation whether on or off board. Our selective impedance control takes advantage of our omnidirectionality, and so we can exert a force or torque in any direction. We choose to be compliant in the direction of contact and reject disturbances in other directions. Local planning involves obtaining a point cloud in the contact direction, calculating the distance and normal vector of the surface, orienting to the surface normal to make contact. And then we travel along the surface in a predefined direction, updating as we go with the orientation. We use state estimation for different experiments, either fully onboard with visual inertial sensing or off-board with Vicon motion capture cameras. Our first experiment demonstrates the behavior of the selective impedance control, with compliance acting on a select axis. We introduce a disturbance by pulling on a rope connected to the system's end effector. This is done with external motion capture state estimation. Now we show a push and slide task of drawing on a whiteboard with compliance in the direction of contact. Here we show that we can reject disturbances from friction forces as we draw. Over a series of 3 consecutive trials, we can accurately and repeatably draw the same pattern on the whiteboard. This is also performed using external motion capture for state estimation. So we further perform navigation on unmodeled surfaces with purely onboard sensing and state estimation using visual inertial sensing. On the right, you see the point cloud, where we obtain a normal vector, which is the long red bar. And this is taken from a selection of points and a Gaussian weighting on this selection of points in the direction of contact. Then we can move along the surface and update our normal direction at 5 Hertz and change our orientation as we navigate. So here we demonstrate the system as a tool for non-destructive testing of reinforced concrete. This concrete block has a known corrosion spot on the underlying rebar. We take 9 measurements at 5-centimeter intervals along the sample, and we hold a force as we take the sample for the electrochemical sensor. Results show that the corroded points are identifiable by the contact sensor, which also shows the viability of assisted or autonomous contact inspection of infrastructure with flying robots. So finally, we evaluate the visual inertial onboard state estimation, comparing to motion capture ground truth, and evaluate the force estimate by pressing against a 6-axis load cell. Over a trial of 90 seconds, we have a root mean squared position error around 1 centimeter and orientation error around 3 degrees. And for force estimation, the error is on the order of 1 Newton. In conclusion, we've presented an omnidirectional platform with selective impedance control for contact inspection and path planning in contact on unmodeled surfaces. In our experiments, we demonstrate the system's capabilities, which are building blocks for contact inspection of infrastructure. So thank you, and I look forward to further discussion at the poster session.
Thank you. Okay. Next talk is on inverting learned dynamics for aggressive multi-robot control, and the presentation will be given by Alex Spitzer, again from CMU.
Hello everyone, my name is Alex Spitzer, and today I'm going to talk about inverse learned dynamics for quadrotors. So the goal of this work is to accurately track a trajectory with a quadrotor. Given a smooth trajectory through space, the objective is to generate the control inputs or thrust and angular acceleration of the vehicle that, when applied, will result in the vehicle accurately tracking the desired path. However, this can be quite difficult in the presence of disturbances or unmodeled dynamics. So we want to be able to react to online changes to the vehicle dynamics. This requires a model learning technique that is efficient enough to be executed in real time. We want to learn a general acceleration model that can be used to improve the tracking of any arbitrary trajectory, and we want to be able to compensate for vehicle dynamics that may be complex or nonlinear. Prior works in quadrotor controls use a concept known as differential flatness to generate control inputs that perfectly follow a trajectory under a known model. We can see here on the left that this requires higher order trajectory information, or acceleration, jerk, and snap, to be available. Using the vehicle dynamics model, acceleration, jerk, and snap are converted into orientation, angular velocity, and angular acceleration. The orientation and angular velocity are used as set points in the orientation feedback controller, while the angular acceleration is directly used as a control input to the vehicle. This work focuses on this nonlinear transformation in the middle, where acceleration, jerk, and snap are converted into orientation references. This transformation uses a simple vehicle acceleration model that is comprised of two terms, and it's going to be shown here on the bottom. The first is the acceleration due to the motor's U, and the second is that due to gravity G. However, this simple model is often incomplete and inaccurate. Additional forces due to payload, wind, or aerodynamic forces or mismodeled rotors render the model inaccurate, which renders the orientation references also inaccurate. This results in poor tracking performance. So in this work, we learn an additive correction to this model that lumps together all other accelerations not considered by the nominal model. Now, using this learned model, we can correct the orientation references. Specifically, by querying the model to 0th order, we can correct the orientation of the vehicle. Many prior works in quadrotor controls stop here and do not use the learned model to correct the higher order orientation references. While this works well for slow flight, accurate tracking of highly dynamic or aggressive trajectory requires accurate higher order orientation references. By querying the model's first derivative, we can correct the angular velocity, and by querying the model's second derivative, we can correct the angular acceleration. The main takeaway is that if your control input is angular acceleration, you really need to look at the second derivative of your learned acceleration model to get good tracking performance. Next, you're going to see a simulation experiment where a quadrotor follows a straight line in the presence of aerodynamic drag. On the top is something we call basic compensation, which only corrects the orientation of the vehicle, and on the bottom is our approach, which fully inverts the learned model, correcting all of the orientation references. Our approach outperforms the baseline method, achieving an error of 3 centimeters as compared to 14 centimeters. The next experiment is a similar simulation experiment, but this time considering a more complex mass and angle-based disturbance. Again, our approach outperforms the baseline compensation with 3 centimeters versus 68 centimeters. We test our approach in hardware using 2 trajectories, a line and a circle. Both trajectories are quite aggressive, reaching accelerations of 6 meters per second squared and reaching close to the vehicle's physical limits. For the line trajectory, we see a 30% average improvement in tracking error using our approach, which fully inverts the learned model when compared to basic compensation, which only corrects the orientation. Next, you're going to see 3 circle trajectories. The first circle trajectory is used for training data to compute the acceleration model. And in this trajectory, the vehicle executes it without using any of the data. As a result, the vehicle achieves a high tracking error. The second trajectory is basic compensation, where the vehicle uses the learned model to correct the orientation of the vehicle. While this improves the performance significantly, because higher order orientation references are not corrected, the vehicle still reaches high error, reaching above 20 centimeters in error. The third trajectory is a trajectory executed using our approach, which fully inverts the learned model and corrects all of the orientation references. This approach further improves the error when compared to basic compensation by about 30%. Thank you, and I left a few things out, so if you want to know more, please see the poster.
All right. As I mentioned earlier, the 5th presenter is stuck at the airport, so I'd like to invite all the speakers up for the Q&A, and maybe they should line up in order. All right. Questions? Yep, over there.
On the paper for on the quadrotor or omnidirectional UAV with the interaction with the environment, how does your work compare with the results by the group of Sami Adaddin or Antonio Franchi doing the same, possibly also without a force torque sensor?
Yeah, that's a good question. So we're taking a slightly different approach by having the platform be body omnidirectional, so that we can change the orientation completely and we model it as just a single rigid body in a sense. So the applications end up being quite similar. What we're trying to extend here is our ability to plan locally by observing the environment and have fully onboard state estimation. So we're focusing on a field deployable strategy as well.
Good. Other questions? Yes, one over there.
For the fourth speaker, what kind of model did you learn and how did you deal with extrapolation where you didn't have training data?
So the model we use is, we use linear regression with the input data projected to a high dimensional feature space. And so for the simulation experiments, we use hand-selected features, where for the hardware experiments, we use simple linear features. And because we use a very simple model, it's the training trajectory actually captures most of the data that will be seen at test time. So we didn't really suffer overfitting, but if you use more expressive features, that's certainly a problem. And I think choosing features is a difficult problem that this work doesn't really consider. So more complicated regression strategies will definitely improve the model and then improve tracking performance.
Other questions? There's one.
This one is for the first speaker. So when you obtain the depth plane parameters, how do you do that and what are the assumptions?
The plane depth is just the given information here.
Okay, so you assume like it can be gotten from point cloud or?
There are many approaches to predict the root parameters, I guess, and even the related works pre-train the single camera depth from the LiDAR. So I guess the competition is quite equal, I guess. Yeah.
Thank you.
Other questions? Let me ask a question to Winnie. Tabib, so in the information-theoretic exploration, do you do greedy strategies or do you do non-myopic strategies for the exploration? If greedy, do you get stuck in local minima? If not greedy, how do you handle complexity?
So we used a combination of a local information reward and a global information reward to try to prevent against getting stuck in local minima. And then we varied the lengths of the trajectories. So there were shorter length primitives and then longer length primitives to try to avoid that case.
I see. Okay. Wolfram, here.
Yeah, I have a question to Yesung. So we all learned recently that LiDARs is a lame technology. So when do you think that with your approach you could actually replace LiDARs? Yeah, Yesung.
I also agree that the LiDAR is very outperform every detection test. So far, I think the camera-based approach is particularly good for the closer object detection, or somehow, people also can drive without a LiDAR, I guess. So far, I guess there are a lot of problems in the algorithm, not the modalities. So I guess this is one approach that we trying to follow what human did, I guess.
Any final questions? Okay, well, thank you very much. This concludes the first session. We'll move on to the next one. Thank you.